Good morning, George Najik here. It's Sunday, September 29th. I have been working on a problem involving charge distributions between two conducting spheres that form a capacitance. Has to do with what's called the proximity effect, that charge will redistribute itself as two charged spheres are brought in close to one another. And in the equations that I came up with, it occurred to me that I could present a problem to you viewers to solve based on some of the equations that I developed on this capacitance distribution problem. And the problem I'm posing to you is this. Given the number y, which is a sum from the index n equals 1 to 2 of, in the numerator we have the hyperbolic sine of the quantity, the natural log of a plus the square root of b, divided by the hyperbolic sine of the index n that we're summing over times the natural log of a plus the square root of b. And the problem is to find the a and b, if you can, so that y is real and rational. That is, y can be expressed in this form, p over q, where p and q are integers. That's what we mean by a rational number. So see if you can find values for a and b that will make y rational and real. So I'll pause here for a moment, and then I will provide you with the solution. So if you want to work on this, stop the video now and work on the problem and then come back. So now I will solve this problem. Okay, well, first what we need to do is we sum over the index n from 1 to 2. So our y then, when n is equal to 1, n here is 1, so the numerator and denominator are the same when index n is equal to 1. So the first term is 1. Now when n is equal to 2, we have the hyperbolic sine of the natural log of a plus the square root of b divided by the hyperbolic sine of 2 times the natural log of a plus the square root of b. Now I'm going to form, to make it a little easier on myself, I'm going to bring the 1 over to this side and we're going to just work on this. So this is y minus 1 is equal to that. And we're going to work on this. Because if we can make this rational, then when we add 1 to it, y will also be rational. A rational plus a rational will give us a rational number. Now rationals are closed under addition. Now, first we need to look at what is the definition of the hyperbolic sine. Hyperbolic sine of x is e to the x minus e to the minus x over 2. This is similar to the complex number definition for sine, where we have in the exponent a unit imaginary I, but when we're dealing with hyperbolic functions, we're just really dealing with real exponents. So that's the definition of hyperbolic sine. So let's look at now the hyperbolic sine of, let's say, the natural log of some number cap a. Okay, cap a in this case will be a plus the square root of b. So we're just going to first look at this. So using the definition for hyperbolic sine, this becomes e to the natural log of a minus e to the minus natural log of a all over 2. Well, e to the natural log of a is a minus, and e to the minus natural log of a is 1 over a. And that's divided by 2, or we can write this as a squared minus 1 over 2a. So that's our hyperbolic sine of the natural log of a is equal to this quantity here. Okay, this is what we have so far, that y minus 1 is this sum, which expanded out gives us this. Now I just computed that the hyperbolic sine of the natural log of a is a squared minus 1 over 2a, and we can see that this is of this form where a would be little a plus the square root of b. Now let's find the expression for the denominator. So we have the hyperbolic sine of twice ln of a, and this is hyperbolic sine of ln of a squared. The 2 on the natural log can get moved over to the exponent. So using the definition of sinc or hyperbolic sine, this is e to the a squared minus e to the minus a, or not quite. Got to get the log function in there. So this is e to the natural log of a squared minus e to the minus natural log of a squared all over 2. E to the natural log of a squared is a squared minus e to the minus natural log of a squared is 1 over a squared, and this is over 2. If we multiply numerator and denominator through by a squared, we have a to the 4th minus 1 over 2a squared. So we can write this now is a to the 4th minus 1 over 2a squared. And we can expand this a little bit. This is a perfect square, so this is a squared minus 1 times a squared plus 1 over 2a squared. Now we need to take the ratio. That is, we're going to have this in the numerator, this in the denominator. So hyperbolic sine of the natural log of a divided by the hyperbolic sine of 2 natural log of a then becomes, we have this, which is a squared minus 1 over 2a, and we divide by this, or multiply by the reciprocal, which is 2a squared over a squared minus 1 times a squared plus 1. And we have some simplifications. We have a squared minus 1 in the numerator and denominator. We have a 2 that cancels, and we have an a that cancels. There's 1 there. So we end up with a over a squared plus 1. So that's the form for sinc natural log of a over sinc twice the natural log of a. Now let's put in for our a, which is little a plus the square. We now have that the sinh of ln of a over the sinh of twice ln of a is a over a squared plus 1. So now we'll make the substitution that a equals little a plus the square root of b. So we're going to work on this. This is y minus 1. So y minus 1 will just be a plus square root of b over a plus the square root of b squared plus 1. So let's expand the denominator out. We have a plus the square root of little b. This is a squared plus 2a square root of little b plus b plus 1. And I'm going to partition this using associative properties. So I'm going to write this as a squared plus b plus 1 plus 2a square root of b. So we separate out the radical from the non-radical part of the expression. Now, remember, we want y minus 1 to be rational, so it's going to have this form, p over q, where p and q are integers. Now, if y minus 1 is rational, then y minus 1 is equal to a rational number, then y is equal to that rational number plus 1, which is also rational. Okay, so if p over q is rational, then y equals 1 plus p over q is also rational. That's what I was just saying here. So this would be of the form q plus p over q. Q and p are integers, so an integer plus an integer. Integers are closed under addition, so p plus q is an integer, so we have an integer over an integer, so y will be rational if p and q are rational. Okay, now let's look at p over q. P over q is this here. We're going to focus on this for now. So let's expand this out, cross multiply. So we have a plus the square root of b times q is equal to a squared plus b plus 1 times p plus 2a square root of b times p. And let's expand this out here. So this is qa plus q times the square root of b. So we've got qa plus q times the square root of b. Now, in order for this to be rational, we have to get rid of the radical on both sides. So this gives a condition that q is going to have to be equal to 2ap. That is a requirement. If q is equal to 2ap, then these cancel, and we're left with a times q equals a squared plus b plus 1 times p, with this condition. If we write this as, for example, we can write this as p over q. This is the top one. P over q is 1 over 2a. But p over q is also a over a squared plus b plus 1. So we have an expression here now. We can cross multiply, and we have a squared plus b plus 1 is equal to 2a squared. And a squared cancels on each side, so we're left then with a squared equals b plus 1. That's the relationship between a and b. So what we can do is we can build ourselves a table now. Write this as p over q. This is the top one. P over q is 1 over 2a. But p over q is also a over a squared plus b plus 1. So we have an expression here now. we can cross multiply, and we have a squared plus b plus 1 is equal to 2a squared. And a squared cancels on each side, so we're left then with a squared equals b plus 1. That's the relationship between a and b. So what we can do is we can build ourselves a table now. Okay, so we had that y is equal to 2a plus 1 over 2a, and we also have that a squared equals b plus 1. So we can now build ourselves a table. We can choose a, and from a we can get b. So if this is our a, then b is equal to a squared minus 1 from here. And a and b will be integers. If a is an integer, then a squared minus 1 will also be an integer. So if a is equal to 2, then what is b? b is a squared, or 4 minus 1, or 3. If a is 3, then a squared is 9, minus 1 is 8. 4 gives us 16 minus 1, or 15, and so on. Now, what is y? Our y then will be 2a plus 1 over 2a. Well, what is 2a? 2a in this case is 4, so this will be 5 over 4. When a is 3, we get 6, so this will be 7 6. When a is 4, we've got 8, or 9 over 8. So, and so on. So, these are our y's. So if a, we can choose any number of an infinite number of combinations for a and b to give us y as a rational number. So if a is 4, b is 15, then y has the rational value of 9/8, and so on. So that's the solution. There's an infinite number of solutions for a and b that are integers that will solve this problem.